So in the previous slides, we have seen that the rate of reaction, we have seen over here, the paths x and y of the concentration terms A and B in the rate law not necessarily equal to stoichiometric coefficients A and B. Thus, x and y are experimentally determined. They are not, you can say they are not theoretical, they are experimentally determined. So here if you see, for example, if you have x is equal to y is equal to 1. Mathematically, if you see anything raised to 1 will be the same value. Laws of mathematics we have seen. So, rate of reaction will be K into active mass of A raised to 1 because active mass of A raised to X. So, that will be active mass of A raised to 1 and active mass of B raised to Y, but Y is also equal to 1. So, rate of reaction will be K into active mass of A into active mass of B. The equation implies that the rate of reaction depends linearly on concentration of A and B. If either the concentration of A and B is doubled, the rate will also be doubled. Because if you see, it is directly proportional, or you can say that the rate of reaction, it depends linearly. Means if one is increased, the other will also be, the other will also increase. So rate of reaction will increase linearly, or it will be increased if either reactant A or B is increased, or if it is doubled. Next case, if you see, if x is equal to 2 and y is equal to 1, then this equation will lead to, again I'll bring you back to the equation. Rate is equal to, if you see over here, rate is equal to K into active mass of A raised to X into active mass of B raised to Y. We have this equation. And now we have the condition that X is equal to 2 and Y is equal to 1. Then the equation leads to rate is equal to K into active mass of A raised to 2, that is, it is power 2, and active mass of B raised to 1. If the concentration of A is doubled, keeping that of B constant, the rate of reaction will increase by a factor of 4. Now why this is 4? Because we are increasing it to double. So if you see again, see, if you are getting confused, I'll bring you back to this equation. Yes. Rate of reaction will be what? Rate of reaction will be K is K into active mass of A raised to X into active mass of B raised to Y. And here if you have X is equal to 2 and Y is equal to 1, then this equation will be K into active mass of A raised to 2 into active mass of B. Now if the concentration of A is doubled, if you are doubling the concentration, then B is kept constant because for B we have coefficient just 1. The rate of reaction will increase by a factor of 4 because you are doubling it. Since you are doubling it and you are raising it to the power of 2, so the rate of reaction will increase by a factor of 4. Next thing, if you have, if x is equal to 0, now according to the rule of mathematics, you all know this, anything raised to 0 is 1. Anything raised to 0 is 1. So if x is equal to 0, then the rate is independent of the concentration of A. It doesn't depend upon the concentration of A. And if x is less than 0, that is, you can say if it is less than 0 means if it is going in negative value, the rate decreases as concentration of A increases. The more the negative value, the less will be the rate. Now writing the rate law. When you are writing about the rate law, how to write the rate law equation. Consider this reaction, 2 molecules of H2O2, that is peroxide, will give you 2 molecules of H2O, which is in liquid state, plus O2, which is in gaseous state. So I'll repeat again this reaction, 2 molecules of H2O2. H2O2 is peroxide. Will give you 2 molecules of H2O, water in liquid state, plus oxygen, which is in gaseous state. If the rate of reaction is proportional to the concentration of H2O2, that is peroxide, the rate law is given by rate is equal to K into active mass of H2O2. So this is rate law. How to write a rate law? Rate law you have to write with respect to the concentration of reactant. So the rate of reaction is proportional to the concentration of reactant. Here the reactant is H2O2. So rate is directly proportional to the concentration of H2O2, or rate is equal to K, which is a constant, into active mass of H2O2. Now order of the reaction. For the reaction A of A plus B of B gives C of C plus D of D. If you have this reaction, If the rate of reaction is given by rate is equal to K into active mass of A raised to X into active mass of B raised to Y, then the sum X plus Y gives overall order of the reaction. We have already seen this coefficients X and Y, they are experimentally determined. They are no longer theoretical, they are experimentally determined, and the sum X plus Y gives overall order of the reaction. What exactly the order of reaction is, whether it is first order, whether it is zero order, whether it is second order or higher order reactions, that we are going to see. So what exactly order of a reaction is? It is nothing but the addition of exponents, or hence overall order of a chemical reaction is given as sum of parts of the concentration terms in the rate law expression. Sum of the parts, here you can say the par is X and Y. So sum of the parts of the concentration terms in the rate law expression. For the reaction, if you consider this reaction, two molecules of peroxide, that is H2O2, will give you two molecules of H2O, which is in liquid state, plus oxygen, which is in gaseous state. So experimentally determined rate law is rate of reaction is directly proportional to the concentration of H2O2. So rate of reaction is equal to K into active mass of H2O2. In the previous slides, we have already seen that X or the par which is raised and coefficients or the concentration 2, 3, 4, they are different. X which is there, this X is experimentally determined. So here also rate of reaction is directly proportional to concentration of just H2O2. So it is a first order reaction. So it is since it is dependent on the single reactant concentration, so it is a first order reaction. If the experimentally determined rate law for the reaction is, for the second reaction, if you see in the second case, H2 in gaseous state plus I2, which is again in gaseous state, will give you two molecules of HI, which is again in gaseous state. So rate of reaction is equal to K into active mass of H2 and into active mass of I2. So the reaction is of first order in H2 and first order in I2. You see, for H2 we have coefficient 1 and for I2 we have coefficient 1. So it is first order with respect to H2 and first order with respect to I2. 1 plus 1, so the overall order of the reaction will be 2. Whereas in the first case, if you see for the first reaction with respect to peroxide, the concentration or the exponent was just 1. So it was a first order reaction. And here in second case, if you see, it is first order with respect to H2 and first order with respect to I2. So 1 plus 1, that will be 2. Key points about the order of reaction. Now this is important. What all key points you should know about order of reaction? The very first thing is order of a chemical reaction is experimentally determined. It is not the theoretical concept, it is experimentally determined. Order can be integer or fraction. Now if you see in the above, in this case, acetaldehyde is taken in gaseous state, will give you methane, which is again in gaseous state, plus carbon monoxide, which is in gaseous state. Rate law for this reaction is found to be rate is equal to K into active mass of acetaldehyde raised to 3 by 2. It is experimentally determined. So here the order of reaction is a fraction, that is 3 by 2. The order of reaction can be 0. Now here, when you have nitrogen dioxide plus carbon monoxide will give you nitric oxide plus carbon dioxide. So the rate expression for this reaction will be rate is equal to K into active mass of NO2 raised to 2. This shows that the order of reaction with respect to NO2 is 2 and with carbon monoxide is 0. So the rate is independent of the concentration of carbon monoxide, and the overall order of the reaction will be 2, because rate here, if you see here, the rate of reaction will be rate is equal to K into active mass of NO2 into active mass of CO. But with respect to active mass of CO, the coefficient will be 0. So anything raised to 0, you are not going to consider, it will be just 1. So it is independent of the concentration of carbon monoxide. So it just depends upon the concentration of NO2. Fourth point, only a few reactions of third order are known. Reactions with higher order are scanty. So we have first order, second order. We do have third order, but they are very scanty. Now we are going to see molecularity of elementary reactions. We have seen order and now we are going to see what molecularity is. Molecularity of elementary reactions. Complex reactions are those which constitute a series of elementary reactions. Elementary reactions means simple reactions that you cannot break down. Just a simple reaction, it doesn't have complex reactions or it doesn't have more reactions in it. A goes to B. This is a element. You can say this is a reaction. Now, when A goes to B via C and D, so this contains a complex reaction. Fine. So, just an elementary reaction, it cannot be broken down into simpler reactions, whereas complex reactions are those that contain lot of elementary reactions. I'll explain you. Complex reactions are those which constitute a series of elementary reactions. What exactly are elementary reactions? If you have ozone in gaseous state, will give you O2, that is oxygen in gaseous state plus simple oxygen. So also if you have ethyl iodide in gaseous state, will give you ethene plus hydrogen iodide. Now these reactions that occur in single step and they cannot be broken down into further steps, they are called as simpler reactions, or these are elementary reactions that they occur in just one single step and they cannot be broken down into smaller reactions. They are called as elementary reactions. Now, molecularity of reaction. It refers to how many reactant molecules are involved in the reaction. If only one reactant is involved, then it is called as unimolecular reaction, or their molecularity is 1. For example, if you have this O3 in gaseous state plus oxygen in gaseous state will give you 2 molecules of O2 in gaseous state. So also if you have twice of NO2 in gaseous state will give you 2 molecules of NO plus O2. Here, the elementary reactions involving 2 reactant molecules are bimolecular reactions, or they have molecularity as 2. The molecularity of an elementary reaction is the number of reactant molecules which are taking part in it. For example, if 2 reactants are involved, or 1 reactant is involved, or 3 reactants are involved, so accordingly you can say about the molecularity of a reaction. Now, what order and molecularity of elementary reactions is? The rate law for the elementary reaction, twice of NO2 in gaseous state will give you 2 molecules of NO, actually it should be NO in gaseous state plus O2 in gaseous state, is found to be rate of reaction is equal to K into active mass of NO2 raised to 2. The reaction is second order and it is bimolecular. The order of reaction is 2 and the molecularity is also 2. For the elementary reaction, for example, if you see C2H5I, which is in gaseous state, will give you C2H4 in gaseous state and HI, which is again in gaseous state. So thus, the rate of reaction is equal to K into active mass of C2H5 in C2H5I, that is active mass. It is unimolecular and it is first order. In the above example, if you see, 2 molecules of NO2 were involved, so it is bimolecular. So also according to the rate law, experimentally it was found out that rate is equal to K into active mass of NO2 raised to 2. So it was second order. Whereas in the first case, rate is equal to K into active mass of C2H5. So it is unimolecular and see, it is unimolecular and it is first order. However, the order and molecularity of reaction may not be same. In the first case, it was not same. So order and molecularity will be same or different. So last thing I'll tell you over here today's lecture, rate determining step. What exactly rate determining step is? Many chemical reactions are complex and they take place in a series of elementary steps. One of these steps is slower than others. The slowest step is the rate determining step. Rate determining step is also called as RDS. Rate determining step is the slowest step. For example, you have seen this in SN1 and SN2 mechanism. I hope in halogen derivatives of alkenes we have already seen this. The slowest step, that step which is slowest and which takes lot of time, that is called as rate determining step. For example, if you have A goes to D, if you have a simple reaction, that is A goes to D, and in this case if you have A goes to B is first step, Then B goes to C, which is second step, and C goes to D, which is third step. For example, if A going to B is slowest step, then that is called as a rate determining step. What exactly is rate determining step and everything we'll discuss in next lecture. Till then, see that you all stay home, stay safe. Thank you.